Okay. So yeah, usually I'm up here talking about data from Cameroon. This is a little bit different. It's a U.S. model. And I'm presenting for Andy Yoak, who's right here with the raccoon. He's an ecologist, usually works on rabies models. But we brought him in with Amy Delgado to work on foot and mouth disease. So this is not the first foot and mouth disease model out there. This is a complex, flexible modeling format like these others that have come before. And it was initially an attempt to modify Interspread Plus to look at human behavior in outbreak control and how that would influence control options. But as we started to work with Interspread, we decided to just write our own model. So this is an agent-based and equation-based model. So the agent, in this sense, a lot of epidemiologists have trouble with that term because agent usually refers to a pathogen. In this case, an agent is some actor, some individual who makes decisions. So the individual here completes commands, and we're using NetLogo software to do that. And the idea originally, agent-based models were developed for things like behaviors of swarms of insects and things that were very complex but based on extremely simple rules. So you give the agent very simple rules and they can result in very complex behaviors and patterns. So this is very useful. It's very intuitive for folks in disease control that somebody makes choices and then that results in disease. So the decision rule concept is easy to translate. And it works very nicely for spatially heterogeneous things and outbreaks where an individual actor can have a huge effect on an outcome. So the stochasticity is quite easy to capture. So this is the punchline of the talk, just to give it to you up front. We did a brief simulation with this model just to see how farmer compliance behaviors would influence disease control. So here are percentages of model runs. The red ones are outbreaks that we consider controlled normally, and then the blue and green are the outbreaks that hit our artificial caps in simulation. So these were the long and large outbreaks, and as you can see, they increase as non-compliance increases. So that's not a real shocker, but we're going to look a little more into how those different non-compliance behaviors might be structured and how that might change outbreak control. So for this investigation, we used the study location of the state of Vermont in the US, and we used surrounding counties just to eliminate edge effects. So the question is, why choose Vermont? It's not our biggest producing state of any sort of agriculture, but it has a very good mix of different production systems for a state in the US. It's predominantly cattle farms, but there are quite a few sheep, goat, and pig farms in the area. Also, one thing that makes it very nice for this agent-based modeling is that there's essentially one company that hauls milk in the area, so the milk route structures are very easy to capture. Another thing for any New Englanders who might be here, Vermont prides itself on its individuality and non-compliance. So it's a good location for this as well. So just to give you some concept of the scale, this is about 60% of the land area of Portugal. And we don't use actual farm locations in the US to prevent impeding on farmers' privacy. So this is a simulated farm location database where farms are simulated in locations in the state with their farm types associated with them. And we use several different pseudo-real farm location data sets to compare for this. So this is a hybrid model. So the agent in this case that makes decisions is the farm, and it makes decisions based on its attributes, which include location, numbers of different species present on that farm, the commodity type of those species, and then the compliance behavior of that farm. So within a farm, we have your traditional compartmental model where we have susceptible, exposed, infected subclinical, infected clinical, and we do let our animals recover if we happen to miss them in the control activities. We also have different species compartmental models running on each farm. So farms are, for the most part, just one species, but there are several multi-species farms, so those would include within species and between species transmissions. So I was very happy to see that somebody's been trying to parameterize those for us. And then the agent-based model component of this is for the farm-to-farm interactions. So we use 5 different types of farm-to-farm interactions that could spread foot and mouth disease. We use local area spread, which is sort of everything that doesn't fit into any other category and is a distance-based kernel. There's the direct transfer of infected livestock, which is based on USDA data. Indirect spread is shared personnel for the most part, veterinarians, artificial inseminators, visitors, and USDA also has some data on that. We did include airborne spread, and we separated out milk tanker spread. So there are some efforts in the U.S. to work on the secure milk supply plan. So we did separate out milk tankers as a possible place for interventions. Okay, so I'm not going to go through the details of these. If anybody's interested in the decision rules for each spread, I'm going to just skip to our compliance behavior. So when we modeled the compliance behavior, this is based on some research that Amy Delgado did. You have all the farms, and then we had nested non-compliance. So approximately 8% of the farms that she surveyed were likely to not report cases of foot and mouth disease if there was no outbreak at the time. So they'd not seen foot and mouth disease, they were not expecting foot and mouth disease, they were not likely to report it. So nested within those, of those 8%, 6%, even if there were an outbreak, would not be reporting. And then the super non-compliers would not adhere to a movement ban if there were an outbreak. So they are subsetted that way. All right. So this is her estimates from survey of what the level currently would be in the United States. So then interventions come into place in this model. So farmers have the opportunity to detect foot and mouth disease on their farms. Once the farms are within a surveillance zone, the detection probability goes up and doesn't depend on this 15 animal estimate. But they have the opportunity to detect it. And then outbreak control, depopulation teams come out as the outbreak increases in duration. More depopulation teams become active and can depopulate a certain number of farms in a day. We have not modeled vaccination at the moment. Okay, so in event of an outbreak, there's a 10-kilometer movement ban zone in red here and a 20-kilometer surveillance zone that go into effect at the site that's been detected. Those give you increases in detection rates and decreased spread from movement of animals and people. It does not affect airborne spread or local area spread. So we did some experiments using this model. And we're varying the location of the start of the outbreak and the commodity type of the start of the outbreak to just do sort of a sensitivity analysis to see what effect those would have on the outbreaks by themselves, and then looking at compliance behavior. So starting location had relatively little effect on outbreak size and duration. So I'm going to keep showing these same graphs. So this is numbers of infected farms in the outbreak and duration of the outbreak in days. And we had these different starting locations. The only significantly different one was this starting location 7, which just happened to be in this very low populated area. So starting commodity type had less of an effect, so we simply changed the commodity type of the chosen starting farm. And it really didn't have a big effect, and that's likely because this was largely a cattle area. So the local area spread took over, hit cattle farms, and then that decided the size of the outbreak as opposed to the starting population. But the degree of compliance really did influence outbreak size. So there's a nice trend that we saw for the outbreaks that were controlled regularly in the model. There's an increasing trend with more non-compliance. We think we're sitting right about at this 8% level. Yep. So here's this graph again. So for those model runs that hit the caps on our simulations, that also increased as you increased your non-compliance. So we looked into that a little bit to see if we could determine what was causing that in particular. We do have infected transfers that occur when you have these larger degrees of non-compliance with the farmers. But for almost every simulation, it's local area spread that was causing the vast majority of cases. And we are concerned that perhaps that parameter is incorrect. It might be dialed up too high. So definitely if we had a lower degree of local area spread causing infections, the non-compliance would show more of an effect, and you'd also have more of an effect of commodity type. So also commodity type didn't really make a tremendous difference in what the outbreak looked like at the end. So there's a lot more work that needs to be done. This was sort of a first investigation using this model to look at compliance. We definitely like to look at patterns of non-compliance. That was what this model was originally made for, to see whether clustered non-compliance or temporal changes in non-compliance would be important factors to consider. We do have a border at Canada that just simply the outbreak doesn't go beyond that border, and we know that's not the case, so we'd like to get some farm data from Canada to fix that edge. We've not implemented tracing or vaccination, which need to be included in here, and we definitely like to adapt this model for other diseases that are currently present in the US so that we can do a little bit more fitting of the model to data. So this is where the parameters are coming from for the most part right now. And the folks who have helped out with this project, we've got our USDA contacts who have helped us with the current USDA data to parameterize these things. Julie Smith at University of Vermont gave us milk truck data so we could figure out the network of milk truck routes, which is very different in Vermont compared to Ohio. Ohio State University is where I am, and we have some students who have helped out a lot in analyzing the milk truck data and building the model, and this is funded by USDA.
Thank you. Given the time constraints you already have, I would quickly like to move on to the next presentation. This is a short one, and if there are any questions,